welcome to the Cosmic Pie Podcast, episode number 42. I'm your host, Wayne Barkhouse, and here with me, as usual,
Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. Yep. Robert, did you notice today's date?
12/5.
The 5th of December. How much snow do we have outside, Robert?
Oh, we have absolutely none.
What do you think of that?
I am kind of concerned.
Well, it's
on many levels.
It's definitely unusual.
It is.
And usually this time we have lots of snow and really cold, but that's not the case now.
It's not the case.
It's actually been fairly mild and no snow to speak of.
Right.
Yeah, it's amazing.
It's kind of, like I said, it's on many levels, it's kind of concerning.
Well, anyways, we'll enjoy it while it lasts. Right?
Absolutely.
And we can't really change it anyways, right?
No.
How do you change the weather? You go somewhere else.
You go somewhere else.
That's the only way you can do that.
The Bahamas are still looking kind of good.
I think they always look kind of good.
Oh, yeah. Oh, right. Yeah.
Well, if any of you have any questions throughout the podcast, please feel free to use the chat feature. Send us our comments or questions that you may have. We'll be happy to answer them. Now, the thing to note, Robert, is this is the final week of classes for us here at the university. Next week will be
finals week.
Finals. So a lot of people hopefully will be studying this weekend. A lot of students preparing for next week.
Hopefully they are.
And then after that, we're pretty well ready to wrap up for the holidays.
Yep.
So I know yourself, you will be going somewhere for the holidays.
I'll be going back to where my family is. So.
Right, and then I will be enjoying the time off as well during the holiday break.
Right.
I have lots of things to do before that, but the holiday break would start at least December 24th. Is that, can I just say that?
Yeah. Hopefully it'll start before then, but...
the way things are, usually working on things right up to the last moment anyway.
True. For me, 22nd and 23rd are travel days, so...
Yeah, so hopefully the weather cooperates. So
that's it.
Maybe the lack of snow will be good for you on this end anyways. It's always a concern during the holidays whether you can actually get out of here.
Whether you can get out of here. The past 2 years, I haven't been able to.
Yeah, well, there you go. So you're due for a good time, right? Now, because we'll be stepping down for the holidays, this is actually going to be our last podcast of this year.
Right.
You're a little sad saying that, right?
It is kind of sad. You get into a routine, you get to where you look forward to these episodes, and then they're done for a little while. So,
but we'll come back fresh.
We'll be back fresh.
Rested.
Here's hoping.
Relaxed.
I don't know about that.
For season number 2.
Yep, season 2.
And the next podcast will be on January the 9th, 2024.
Right.
Do you remember when the year 2000, all the celebration that occurred?
I do. I remember it well.
Yeah, so here we are going in 2024 now.
We're almost a quarter of the way through another century.
So how are we going to celebrate when we hit the year 2100? Are we going to be able to celebrate? Oh, wait a minute. We do the math.
Hey, I plan on being around.
Yeah, we'll see what happens there. Right?
Yeah, we'll see how that works out.
Anyway, so our next podcast will be on January the 9th at 3 p.m. Central Standard Time, as always. So we're not going to change the time, and it'll still be on a Tuesday afternoon. We'll just take a few weeks off here for the holidays and recharge our batteries, as they say.
Right. Look for more good stories.
That's
more
right.
People to bring on to join us.
Exactly. So we'll have lots of things to talk about at that point. So there's been a lot of stuff in the news. In fact, Robert, in some sense, the podcast has been dominated by news coming from the James Webb Space Telescope. And that was launched on Christmas Day. That would be almost 2 years ago. This Christmas
Has
will be
it
2 years.
been that long?
Yeah.
Wow.
It's amazing when you think about it.
It is.
So, and that was exciting. I remember watching it on TV, watching the launch. So what are you doing on Christmas Day? Opening gifts and watching the launch of the James Webb Space Telescope.
And going about time.
Well, that's true. It was delayed a lot, and it was just a coincidence that it was ready to go at that moment.
Right.
Everything, the stars lined up, should I say?
Well, the moon and everything else, the clouds, and I don't know about the stars.
Well, since that time, of course, the James Webb Space Telescope has provided us with lots of things to talk about, and that's the case even today. In fact, our first item that we'll look at is regarding observations recently of some very dusty, distant galaxies.
Mm-hmm.
And these dusty, distant galaxies are unusual in the sense that they have number one, a high abundance of dust.
Right.
In fact, they were first detected not from an optical telescope, but using devices that can look in the far infrared, almost in the radio, the millimeter sort of wavelength of the
microwave.
Yeah, so the microwave part of the electromagnetic spectrum, and that includes the use of the ALMA rays. So we had mentioned this in the fact that's a radio interferometer, a radio array that's located up in the Andes Mountains in Chile, and that looks at the millimeter, sort of sub-millimeter range. And so you're looking at this kind of data or some information anyways that you would see, if you're trying to understand things like star formation, for example.
Right. Because that's where a lot of the heat from the collapsing clouds is given off.
So this particular galaxy that you see the image on the right, that dusty galaxy, that's at a distance of about 12.5 billion light years away from us.
That's a long way.
So if you think of the universe as being around for about 13.8 billion years, that means we're seeing this object as it was about 1.3 billion years after the formation of our universe, the creation of our universe.
Mm-hmm.
Now, of course, we always wonder, well, where did our universe comes from, right? Come on, Robert, let us know, please. We're dying.
I'm just going to say we have no way of probing what happened before. We're still trying to probe to the moment of. So before is its own thing.
If you don't know in detail about science related to what we're talking about, you might wonder, well, you guys, you got these nitty-gritty details of all these objects you can look at with all your instruments and so on and so forth. And yet when I ask you, where did the universe come from? What happened at the moment of the Big Bang? You're like, you throw up your hands. I don't know, beats us. So why is that, Robert? Why is it that we can know things so well this side of the Big Bang, yet when we talk about the moment of creation, somehow we just have nothing to say? Why is that, Robert?
Science at its root is kind of the philosophy of measurement. And if you can't make a measurement about something, it's not science. I mean...
Well, let's broaden that out a little bit here. And we got lots of time today, right? There's no rush to go away.
Right.
So what do you mean by measurement, and what do you want to measure?
Basically, we want to measure as much as we can. We want to put a number to it. We want to quantify. So I know that makes it sound like we're always putting things in boxes, but most things do fit. So, we're looking, how many meters is that? How much mass is that? How much time is that? And so forth. Oh.
What else? What's another thing you can look at would be the temperature.
The temperature. Thank you. I would miss that one, but yes, the temperature.
Right. Yeah. So in other words, to study something in detail, one of the things you could do is look at all the various properties that it has.
Right.
And to describe those properties, a lot of it will be motivated through observations.
Mm-hmm.
And then, of course, you bring in theory, our understanding of how maybe one property is related to some other property,
right,
from a point of view of mathematical relationships or laws or theories that we have, to try to dig down even deeper,
right,
into a more all-encompassing view of what's actually happening, whatever we're looking at. For example, how do you characterize the very, very, very early moments of the universe itself? We have the Big Bang Theory, correct?
Right.
But there's one thing the Big Bang Theory doesn't tell us, which is kind of weird when you think about it. It doesn't tell us why it banged, what banged, or what happened before it banged.
Right. But our tools, like I was mentioning, our tools, our rulers, our meter sticks, our thermometers, can't even quite get us yet to the moment it happened. So we still have doubts about what's going on there. So before is kind of a moot question. We got to get to it before we can go beyond it.
Well, here's a thought experiment.
Okay.
Back in the 1920s, it was observed that the universe is in a state of expansion.
Right.
And that's the discovery that Edwin Hubble and others were involved in.
Mm-hmm.
So that's been in roughly 100 years now. We've realized the universe is in the state of expansion, which means if you go back in time, you use your thought experiment here.
Smaller, denser, hotter.
Yeah, smaller and denser. And along with how we know matter operates, just from what we can test around us locally, it also gets hotter. And I always like to use the analogy that, after the long winter here in North Dakota, you go to jump on your bicycle in early spring to take it for a spin, let's say, and the first thing you notice is the tires are flat from sitting around in your garage, let's say, all winter.
Right.
So you want to put air in those tires. So you pump the air full of, the tires full of air to get it to the right pressure that you need it. And if you quickly grab the side of the tire, you'll notice it's a little bit warm.
It's warm, yeah.
And so we know you've increased the density of the air inside the tire, and along with that was an increase in temperature.
Mm-hmm.
In fact, you can relate these things together. We have fancy terminology, thermal physics, thermodynamics, that relates how if you change the pressure and the volume, what happens to the temperature, and
Charles' law, Boyle's law, ideal gas law.
Because we have all that because these are things we can hold with our hands and we can manipulate, right? And get understanding of the different relationships, and then try to puzzle where do those relationships ultimately come from, motivating eventually the atomic hypothesis that things are made from atoms. You think of the ideal gas law, little tiny constituents of molecules and atoms and so on.
And then you get into all the statistical thermal, that those atoms bouncing around against each other and their kinetic energy gives rise to what we call temperature.
Right. So you can take all that formalism, all that structure, all of our understanding of those type of things, and just apply it to the universe as a whole.
Right.
So as we go back in time, the universe becomes denser and hotter and denser and hotter. The temperature goes up and goes up and goes up and goes up. And eventually you come to the very beginning. And the value we get for temperature is infinity.
Mm-hmm.
And we know there's no such thing as infinite temperature.
And we get infinite density.
Yeah, so it's a nonsensical answers to describe the properties of the universe.
Right. I agree.
That clearly tells us then our understanding of what we've used locally around us breaks down.
Breaks down at some point. The question is how does it break down? When did it break down? And so forth.
So as an astronomer / physicist / astrophysicist / taxpayer / a person who likes to think, if you put all of that together and someone comes to you from the street and says, Robert, what happened at the moment the universe began? What were the properties like at t = 0, assuming time began at the beginning of the universe? And your answer is?
I don't know.
And it's like, wait a minute, right? We've had hundreds of years since the time of Galileo to understand the universe around us, and even prior to that.
Right.
And that's all we can say then at t = 0? That's because our known laws of physics break down.
Break down.
In fact, it is similar to if you were to describe exactly what's happening at the very heart of our black hole.
We don't know.
And that's why we call it a singularity. In math, we have singularity. Those are usually points if you're doing various things which go to infinity.
Dirac delta functions.
Yeah, I was thinking of contour integration and these kind of things. Right? For those of you who know a little bit about math, you'll understand what I'm talking about here.
Right.
You want to avoid those areas because our understanding breaks down. We can't describe what's happening at those specific exact locations. And we just like we can't describe what happens exactly at the very heart of a black hole, we can't describe exactly what happens at the very beginning of the universe. But like the black hole example, we can describe the properties of a black hole outside of that singularity.
Right.
I mean, we can talk about time dilation. That is the slowing down of time, someone near the event horizon of a black hole relative to someone that's much further away. We can talk about gravitational tidal forces that are at work. You can talk about all this kind of stuff, and you don't have to worry about what's happening at the very heart of the black hole because this is outside of that region.
Right.
Just like in the Big Bang theory, we can talk about what happened, a very brief moment of time after the universe formed, and from to this day to the present, but we can't say what happens at exactly the t = 0 point.
T = 0, who knows? And in fact, it's several microseconds afterwards that we can start saying anything because before that point, it's just too hot. The laws of physics break down.
Robert?
Yep.
Did God create the universe?
I'm not going to go there.
Now, from the point of view of science, we always say don't bring religion into the discussion,
Right.
correct?
Correct.
So we stick with scientific principles.
Right.
And what does science say about the exact beginning of the universe?
Not a thing.
So what are you left to look at or speculate about?
Now we're into philosophy and all of that sort of thing.
And religion.
And religion, yeah.
So you're free to say whatever you want.
Right.
Right? If you
I'll
think
agree.
God created the universe, then that's fine, right? What does science have to say about that? Absolutely
nothing.
nothing. There's nothing we say about that. There is things we say about where our laws of physics are valid, but science neither proves
Nor disproves.
nor disproves the existence of God.
Right.
You know, and people ask me that, why it's important, because when I teach astronomy, talk about cosmology, the formation of the universe, I have many students ask me, do you believe in God? And the way I always answer it is, well, from the point of science, I don't believe in anything from science. I like to see the data and the relationship and how things are consistent with one another or whatnot, right?
Right.
Just because, you know, it's like someone saying, do you believe there are magnets? Well, I don't know. I have to go look, see if there are magnets. You know, it's the observations,
It's
right?
the observations.
It's the experiments. But when we talk about things like religion and philosophy, a lot of it is what you believe in. It's a belief system. Science is not a belief system. To a point. Now, you can be a little picky here, and philosophers will do this, and state, for example, do you believe the laws of physics that we know and love locally, things that we can deal with in our laboratory here on the surface of the Earth, are these the same laws of physics that work in this galaxy that's 12.5 billion light years away? Do you believe that the laws of physics are valid as we know them around us here?
And those are called assumptions.
Well, and then the thing you look at is, no, I don't believe. It's not a belief system. So what I do is I could look at an object like this, maybe look at its spectrum. And if I see the familiar lines in the spectrum that I see around objects that are much closer, the object itself, the spectrum in this case, looks like it should look based on the known laws and physics.
That we know locally.
Yeah, then there's no belief system involved.
Right.
I have to make the observation to see if that's true. In fact, historically, people have suggested that maybe over large range of time, like back in the early history of the universe, different laws of physics that we have today didn't operate exactly the same way. And you can actually put some constraints on that of how things might have changed with time by looking very carefully at the things that we can see from the Earth, things around us. And that's been done many, many, many times. And what we could say today, here on December 5th, 2023, is that there is no evidence, absolutely no evidence at all, that any of these laws of physics have changed in the distant past from what they are around like today in our present.
Right. So that's where I was going to go with it. There is no evidence. I mean, it's been tested. We've tried to find differences. And so that leads up to Extrabulla's question did physicists ever figure out through the data from JWST if the universe is actually older than previously thought? And the answer is that's still under debate, from what I understand. But the answer is probably no.
Yeah,
it's not older than what we thought.
Now, first of all, for those who don't know, let's mention what we thought. And the current best estimate of the age of the universe is about 13.8 billion, with a B, years.
Right.
13.8 billion years.
That's old.
Now, has that idea changed since the observations from the James Webb Space Telescope? The answer is absolutely not.
Right.
The reason for that is because James Webb Space Telescope really can't say a lot about the universe as a whole, that is cosmology. It was designed and it can do really well understanding what galaxies were like in the very early part of our universe. So what it can actually do is change our ideas of how galaxies formed to begin with.
There you go.
In fact, before JWST, we thought it would take, billions of years for galaxies to form. But we know that's not the case. We've seen galaxies now that have formed that are about 300 million years old. So what JWST observations really did is upset a bit the apple cart of galaxy formation, but has not even tilted even a little bit the cart that would be the structure and the nature of the universe itself. That has remained as it is, regardless of what you hear. Because we're scientists, we're trying to look at everything with a critical eye.
And I know there's been a lot of scientists that are in popular culture that have said it did. There is no evidence that it has upset cosmology at all, because that's not what JWST was designed to do.
Yeah, and those type of opinions, even though they came from scientists, have not upset cosmology, they've upset cosmologists.
Right.
Because there's a lot of evidence, supporting evidence, for the universe to have the age that it does. And none of that evidence has gone away because of the results coming from the JWST. So galaxy formation, yeah, has a lot to tell us. In fact, it was designed to uncover the dark ages of the universe, the time before galaxies, got around to forming and lighting up the universe.
And lighting up the universe.
We want to know how that whole process of galaxy formation carried out, the details, and that's exactly what JWST is providing today.
So it's functioning as intended.
It is. It's fun. And it's nice that it's not consistent with the ideas we had. Imagine you sent up the JWST and the only thing it found was it agreed to everything that we knew prior.
I would be disappointed.
Yes.
That would be absolutely disappointing that it confirmed everything. I mean, how do you write up a paper? Yep, it's just what we thought.
Well, it's not as exciting if you had some, groundbreaking result that you discovered.
Right.
Because if you're just confirming everything, that's great. You're confirming things, but you're not going to win the Nobel Prize for that.
Right. And I've tried explaining that to many people because they start getting off on scientists, the consensus says this because science has just decided to say that. And it's like, you don't make a career in science by following the trend. You make it when you break the trend, when you say something and can demonstrate that it's true that goes against what we thought we knew.
I immediately think about the quote we read many moons ago from John Wheeler.
Okay.
And to paraphrase him, John Wheeler was the person, he was a Princeton University professor who coined the term black hole.
Okay.
And John Wheeler made a statement regarding, progress in science really comes when you look at those things that are away from the norm, that are different.
That are different.
Trying to understand why they're different.
Right.
And that could, offer hindsights into physics that have been unexplored at this point. And we're always looking for things that are different, not looking for things that are the same.
We want to break things.
Yeah, exactly. And so it's a good thing then. Anyways, it reminds me of the Large Hadron Collider.
Right.
So the Large Hadron Collider, which has been operating for many years now, believe it or not, it was built to look for the Higgs boson.
Higgs boson, right.
So the quanta of the Higgs field, as we would say, in quantum mechanics. It gives rise to the masses that we see particles that they have, right?
Right.
A very, not too accurate, but at least a very simple analogy would be, for example, trying to get through a crowded field in a let's say a dance or something, right? So you're in a dance hall and it's full of people. They're all up on the floor dancing, and you need to use the washroom. And the washroom, of course, just happens to be on the other side of the room from where you are. So you're making your way through those crowds of people. They put up a resistance, right? You have to go around them. Maybe they know you, so they stick out their hands to shake hands with you and give you hugs. And yet you want to get to the washroom as fast as possible. But compare that sort of resistance to if there's nobody there. It's 3 hours before the dance starts, and you need to use the washroom. Well, then you can just go right across the floor and use the bathroom without being interfered with.
Or if you're a ghost, you can just go right across.
So that and you can, and that brings up another issue with that. So when you go across the dance floor and people are in the way, that's like you have a pseudo mass, an effective mass. Mm-hmm. And when there's nobody in the way, and you mentioned, or you're a ghost, it's like you have no mass. So particles that were originally called ghost particles were things called neutrinos. We thought at one point they did not have mass, so they would not interact with anything else because they had, from gravitational force.
Because they had no mass.
Because they have no mass. Now we know today that's not the case. We did see interactions. Mm-hmm. In fact, they changed one flavor to another. Maybe someday we'll go down that rabbit hole of looking at neutrinos.
Right.
There's a lot of interesting physics there. That we know neutrinos have a little bit of mass, so they do, have an effect, to have an interaction with the Higgs field.
Right.
So the Large Hadron Collider, the billions and billions of dollars, euros really, because it's in Europe, that was spent, building this thing, it found the Higgs boson, as we would say, but it hasn't found anything else, essentially.
Well, it was designed to look for the Higgs, so...
But at the energy required to slam particles together, and these are protons slamming into protons, not only should we have found the Higgs particle out of those type of interactions.
Oh, I get where you're going. Okay.
But we should have found lots of these other types of particles called
the other
supersymmetric particles.
Yep.
And supersymmetric particles, at least what we want to get into today, are really needed if our ideals like string theory are correct. String theory is this ideal of putting together both quantum mechanics and gravity, general relativity, into an all-encompassing theory that maybe will tell us what goes on at the center of black holes, and maybe will tell us what happens at the very moment of the beginning of the universe itself.
Right.
And those particles have not been found.
Right.
So,
which has a lot of people worried.
well, so particle physicists are writing papers today giving upper limits.
Right.
Right, on particle. Oh, we haven't detected. We know it's not of this mass range or energy range, which is equivalent, because we would have been able to detect it. So it must have a much higher mass or greater energy, and we just can't reach those energies. So let's keep running the machine to build up, the counts, the statistics, and maybe we'll get lucky and a very rare event will happen and we'll detect it. But so far,
So far, it's not
nothing.
there.
And that's getting people to wonder, are there even supersymmetric particles around? Do they really exist? Because, our ideas of this uniting of quantum mechanics and general relativity almost demands that they should exist.
Right.
But you can always hide things. It's like peeking under a blanket looking for an old sock, right? If you go under the blanket, let's say by a foot, and you don't find an old sock, it doesn't mean it's not there. It's just a little bit further underneath the blanket than what you thought. You see?
Or it's under a different portion of the blanket.
Exactly. That's what I'm getting to.
Okay.
So it's maybe at higher energy, these supersymmetric particles.
Right.
But at some point, you run out of the available space you can search.
Sooner or later, you're at the foot of the bed.
You need a bigger machine, right?
Right.
So, in other words, you need to crawl underneath your blanket a lot further to look for that sock.
Okay. Yeah.
So if you need a machine that can deliver more energy in collisions, where do you go get the money to build that machine?
Well, considering we're up to the point now where to build it, we really need to put it in space, and a particle collider in space.
Hello, government, please hand me this money. I need,
Right.
instead of $20 billion, I need $20 trillion to build a large machine. Are you going to get that?
No,
Not anymore.
not anymore.
So I kind of reached the limit, especially when you look at the United States with our national debt of 33 trillion and climbing, almost 34 trillion now. Are you gonna, is the government gonna hand over $10 trillion to build a particle collider?
I'm going to go out on a limb and say probably not.
In fact, if you're a politician and you campaign on the idea that you're going to send $10 trillion to build a particle collider, I don't know if that actually increases your chance of getting elected. It will from particle physicists. They'll all be voting for you.
They'll be voting for you, but yeah.
But that only represents a very tiny, tiny fraction of the total population, obviously. Yeah, so there are problems here.
Right.
You can hide things, but in fact, you have to do the experiment. So if you can't do the experiment, you're kind of stuck. And that's why I think going forward, so here's a prediction from me, Wayne, making this prediction, okay, on this date.
Okay.
And my prediction is this, that going forward, particle physicists are going to become a lot more interested in cosmic rays.
And cosmology.
And you know why cosmic rays? And first of all, Robert, could you define cosmic rays for our listening audience?
Cosmic rays are high energy particles coming in from outside the solar system. They've penetrated the sun's magnetic field. They're, like I said, they're charged particles, so that's important. And they slam into the Earth's upper atmosphere at high enough energies that they create a cascade. They're going near the speed of light. And they create a cascade, just a rain shower of particles, because they break everything in their path. Few of them actually make it to the surface of the Earth. They've got so much energy.
So you're charged particles, so you're thinking like ordinary things you think of, like protons.
Well, I'm also thinking in terms of you can get some heavier nuclei.
And electrons. Anything that's dropped. You can think of atoms that have one or more electrons stripped away, right? Become overall negatively charged. Or maybe you have electrons that have added to the object and become positively charged, right? So you can have various ions of various forms. Now, for cosmic rays, did you hear of almost the GOAT of cosmic ray impacts? It's just
Something was said recently, and yeah, it came from outside our solar system for sure. I haven't heard much more than that, but it created quite a stir because it packed such a punch. It had so much energy that nothing like it had ever been seen.
It was the second most energetic event that occurred
Okay.
in the history of
thought it
observing
explained
cosmic
it.
rays.
I thought it had explained it.
No,
But
it was very close to equaling the most.
for those that aren't in the know, the most energetic cosmic ray that's ever been observed had the energy of Major League Baseball fastball pitch striking you. So a 100-mile-an-hour fastball hitting you in the chest. It had that much energy. Okay, yeah, so what? That's not a whole lot. Yeah, this was a particle. This was an atomic nuclei. This was an atom that packed that big of a punch. So this is a big deal.
And it's
how
always been a mystery, of course, is where those high energy particles come from. Where do they originate?
That's a good question.
There's nothing in our solar system that can produce that type of energy.
Absolutely not.
The energies are huge. I'm trying to think of the actual values, like on the order of 10 to the 19 power in terms of electron volts or something like that. But
Right.
it's just, huge amounts of energy. But why then would particle physics turn their attention to cosmic rays once we've used the LHC to its fullest?
Well, because that's where you can get particles flying at higher energies.
Much higher energy.
Much higher.
Way higher than what the Large Hadron Collider can provide today.
Right.
In fact, we have a free particle collider.
Yep.
We don't have to spend any money per se to build it. It already exists in nature.
Oh, and the neat thing is we're looking at the cascade of particles that come from the collision anyway. So the cascade of particles from a cosmic ray hit fall right into what we're looking for.
Exactly. So you study the interaction of these high energy particles, these cosmic rays with the atmosphere on the Earth to be able to give us some information about what happens in these very, very energetic collisions. Ones which you would never be able to reproduce here on Earth because there's no government going to give you that amount of money to build a machine that would manufacture these type of collisions.
Right.
Now, the disadvantage is the collisions come in very rarely.
Right.
So it's going to take a long period of time to accumulate enough information to say anything definitive.
And you don't know where.
Yeah, that's it. So you got to be looking all the time. But the thing is, you also don't have to spend $10 trillion.
That's good. Yeah. Yeah. I would like not spending 10 trillion. Yeah.
Well, if it's not available, it's not available.
Right.
So you do the next best thing, and is to turn your attention to cosmic rays. So I predict that that's going to be an explosive field, no pun intended, going forward in the next couple decades. You're going to get a lot more scientists studying cosmic rays and their impacts, potentially building a lot more sensitive detectors here on the ground, which could be done a lot cheaper than $10 trillion.
Right.
And use that as a way to try to figure out, this physics that occurs on this such energy, high energy scales.
Makes sense to me.
Yeah, it's really cool when you think about it. Now, Robert, there's been other news out there that's not directly related to the James Webb Space Telescope. I know that's hard to imagine.
What?
But if we're gonna, before we turn off this, if we want to go to the next, okay.
Okay, the next one?
Yeah,
Okay.
I was gonna go. I just want to make a point on this slide here. So the panel on the right actually gives us a way of uncovering very distant objects. Now,
Okay.
because the universe is in a state of expansion, all objects beyond the ones in our backyard, I mean galaxies, let's say, so forgetting about the nearby galaxies, every other galaxy in the universe is moving away from us. And the further a galaxy is from us, the faster it's moving away. And that's because of the expansion of the universe.
Right, because you're stuffing more space into space.
Yeah, so if you think of some length of space, let's say 1 light year, if that light year of space is getting larger every day by a little tiny amount, well, the more light years of space between you and some distant object, the more that space is increasing, every day type of thing.
Yep. I've always heard it, and this is a bad example, don't get me wrong, but it's like raisins in a loaf of bread. The further they were apart originally, the further they're going to be apart as the bread starts to rise.
I always heard of that too.
It's a bad example.
Well, here's the example. Kinds of a little weird nowadays because I don't think a lot of people have exposure to watching a raisin bread cook from scratch.
That's a good point too.
That example comes back from the early 1900s when
Right.
people were making things in homemade things all the time, not going to the store and buying it dirt cheap, which you can do nowadays, you
Right.
see? Right. Anyways, so I like to think of like a rubber band. And let's say you cut a rubber band loop, you cut it so you have just one length. and you were to put, let's say, 2 pins in it spaced out a certain distance apart, and you could ask the question, how can I move those pins in such a way they move away from each other without touching them?
Well, you stretch the rubber
You
band.
stretch the rubber band from both ends. So you pull the rubber band apart, and that naturally, because of the rubber between the 2 pins, naturally increases the distance between them. And the pins themselves don't physically go through the rubber band and cut slits or something into it.
Right.
So that's the analogy here with galaxies moving away from all other galaxies because of the expansion of the universe.
And the more rubber band between them, the faster they move
faster
apart.
move away. So we know that distant galaxies that recede faster than ones that are closer to us. So if we look at something that's really far away, all of its lines, if you look at the spectral features that normally would appear in the optical for an object that was close by or one at rest relative to us, have been shifted redward to a much longer wavelength. So far, in fact, a lot of that optical spectral features are shifted way off into the infrared.
Right.
In fact, the James Webb Space Telescope, which is an infrared telescope, was designed initially by cosmologists to study the very distant universe.
Right.
And because these spectral features that we know and love in the optical from nearby galaxies are shifted to the infrared, they wanted to look at things in the infrared.
Right.
And in fact, as you see here on this figure on the right, the panel, what you're looking at is the same galaxy, this dusty galaxy, observed at a much shorter wavelength, closer to the optical, still in the infrared. And that's you look at the panel on the right, this is the postage stamp on the far left of that panel. And as you make your way, it has a number above it, you see it F115, so that's roughly at 1.15 microns, so it's in the infrared. And as you progress to the right in that panel, as you look further at the mosaic, let's say the one that's to the right of that, that's F150, so it's a little bit longer wavelength. You still don't see in the 115 and the 150 image, you don't see the galaxy in the center. But once you get to 277, so that's 2.77 microns essentially, much further in the infrared, there's the dusty galaxy in the middle of the postage stamp.
Right.
In fact, as you continue to go to even longer wavelength, 444, so 4.44 microns, it's easy to see in the middle.
Right.
So in other words, at shorter wavelength, this object was essentially invisible, and you had to go to longer wavelengths to pick it up. Because if you look at how the light is distributed as it relates to wavelength, because of the redshift, most of the light, that is, the galaxy is the brightest at wavelengths that are in the several micron wavelength range.
In fact, that's getting close to mid-infrared.
Mid-infrared. And so it's interesting that if you just restrict yourselves to optical, you wouldn't even know that galaxy existed.
So Hubble wouldn't even see this guy.
Now, the other thing affecting the redness, of course, is the fact these are dusty galaxies.
Right.
And dust will make the color look red. All you have to do is look at the sun, even at local noon, when there's a lot of forest fire smoke in the air, like in the summer times around here, and the sun can look really red.
It looks really red, yeah.
And what's happening is the other shorter wavelength photons have been preferentially scattered from the line of sight from us to the sun, leaving the longer wavelengths that can more easily penetrate through that smoke and through the rest of the atmosphere, being the oranges and the red. And so it gives an overall red color to the sun. Same kind of thing that's happening here. So it's a combination of the redshift and the fact that the galaxy is dusty.
It's dusty.
To make it look unusually red.
Okay, I can buy that.
Yeah. So, you need instruments like James Webb to be able to look at these wavelengths outside of the optical to get a good handle on these type of objects. And the next thing you would look at, of course, is why is this thing dusty like it is?
Right.
Why does it have a large fraction of dust compared to other more normal galaxies? And that's some of the stuff that you can explore. And some of the things you look at, if there's a lot of star formation happening early on in the history of this galaxy, and remember this galaxy as we observed it is about 1.3 billion years after the universe began. Maybe this galaxy, when we see it today, has been around, that is, when we look at it today with our telescope, has been around for about 1 billion years. Well, you can form a lot of stars in 1 billion years. In fact, high mass stars only live all total a few million years. So you could have multiple generation of stars that form, especially the high mass ones. And what happens to them at the end of their lives is they blow up as supernovae. They can eject a lot of dust into space. So these galaxies, these dusty galaxies like this one, maybe it has accumulated a lot of this dust from these earlier generation of these high mass stars, a lot more so than what a normal quote unquote galaxy would accumulate at this point in its history. And that's why these are particularly dusty versus other type of galaxies. So definitely a lot more follow-up work for these type of systems.
James Webb's still got a lot to do.
Okay, Robert, what else has been in the news lately?
Well, we found out about an impossible planet.
Impossible planet. Hopefully it's not Earth.
No. Well, that remains to be seen. We're still checking into that. But this one is a planet that is far too large, far too massive, I should say, for the star it's going around. So it's a Neptune-mass star, so a fairly Neptune-sized planet going around a very small star, an M dwarf. We've mentioned those before. So what does the M dwarf mean? What does it mean that it's a small star? It's roughly, I think, a third the mass of the sun, I think.
About a tenth. This one's about a tenth.
About a
0.1
tenth.
solar masses, yeah.
Okay, so it's about as small as you can get and be a star.
Yeah, so the theoretical limit on the lowest mass object you can get and still be a star is about 8% of the sun's mass.
Right.
So 0.08 solar masses.
And this
This
is
one's
0.1.
barely above that at like 0.11 or something, right?
Right.
Is the estimated mass. So
So-
yeah, very, very low mass star.
Very low mass star. Essentially, this planet, expanse-wise, would be as big, almost as big as the star, radius-wise. And, mass-wise, it's still much smaller than the star. But because of compression and everything else, radius-wise, it's actually on the order. It's got to be getting close to the size of that star. But anyway, that's beside the point. This goes against all of our knowledge of planet formation. So go ahead.
I was going to say, did you notice how long it takes this planet to go around the host star?
I did notice that. Thank you for stopping me. Yeah, 3.7 days.
In fact, if you go to the next slide, I think we have a table that you can take a look at. And some of the important facts are on the right of that table. So 3.7 days to go around once. So it's very close to the host star. It's not like it's way, way far away, like, relatively speaking, the distance that Jupiter, several AUs away from the sun type of thing. This is really a lot closer.
Really close.
Lot closer than Mercury, for example.
Right. And yeah, 3.7 days. I can also make some comments that given how active M dwarfs are and everything, this thing is essentially bathed in the outer atmosphere of this star.
So it's not the first place you would select as a vacation spot in the future.
Oh, heck no. Talk about those cosmic rays. There'd be a lot of energetic particles simply from the magnetosphere of that star passing through the atmosphere.
Now, when we think of the mass, we said it was a Neptune-like mass, but what does that really mean if you don't understand the mass of Neptune? So it's on the order of about what?
About 13 to 15 times the mass of Earth.
Right, so that gives you a good idea, maybe a better idea of how massive this. So you have a massive exoplanet that's orbiting very close to a very low mass star. Now, Robert, what is so wrong with that? Obviously, it happened. We found it.
Right.
So why would that be unusual?
Several different reasons this is unusual. One is that there shouldn't have been enough leftover debris, leftover gas and dust from the star forming to have formed a planet that massive. There just shouldn't. Basically, the upper limit we thought was that the debris disk had about a tenth of the mass of the star, and only a portion of that is going to go into making planets. So, a very small fraction, as a matter of fact. So, you've already talking about a tenth of, 10% of the mass of the star going into possibly being available to make planets, and you've got this big, massive planet formed out of this that should have been very little. So anyway, the point is there shouldn't have been enough material left over from forming the star to form this big of a planet. That's one of the big things.
Now, I assume that a lot of that information, that ideas of how planet forms, is obviously biased heavily from our own solar system.
Right. I mean, one of the big things we're looking for, honestly, is a solar system like ours. Because who doesn't want to find that there's life out there?
I know. I remember just a few decades ago, I'm old enough to remember that, right? Just a couple decades ago, before we found the first confirmed exoplanet,
Mm-hmm.
that people speculated, some astronomers, that, solar systems, you would think of the average property of a solar system, it would have like 9 planets.
Right.
And maybe there'll be like, 4 or so be gas giants, and you have about 5 of them, these rocky planets, and then so on.
Look
But
very much like ours.
But we
yeah.
don't even have 9 planets today, right? They
Right.
got rid of Pluto since that time, you see?
Well, I
That's a
would argue
dwarf
we've got
planet.
a whole lot more than 9 planets.
Well, that's it. Right?
Because Pluto wasn't, nobody said Pluto wasn't a planet. They just now say it's a minor planet,
A dwarf planet.
a dwarf
right?
planet.
Yeah.
Okay, so it's still a planet. It's just a dwarf planet, a minor planet.
But even if we don't think about Pluto and it's, it's stripped of rank, why should any other solar system in the universe look like ours?
And the answer is there's absolutely no reason whatsoever.
And I can mention one person's name in this discussion,
Okay, which one?
Copernicus.
Copernicus. Okay.
How does that involve this discussion?
I don't know on Copernicus.
The Copernican principle.
Oh, nothing special.
Yes, exactly. There's nothing special about us. And the moment we think there's something special, that's when we go wrong. We go
Yep.
astray. So we had the idea that the Earth was the center of everything. Why? Because that's where we live.
Right.
And we must live on a planet, where it's the center of everything. The center of the solar system, center of the universe, center of the galaxy. All those things turn out to be wrong.
Mm-hmm.
So the Copernican principle is the realization that, you're just average in some sense, right?
Right. In fact, that's what we found. Is the sun is just an average star.
Exactly. And our galaxy is an average galaxy. There are lots of other spiral galaxies similar to our own. Look at the Andromeda galaxy,
Look at Andromeda.
for example. And there's lots more, throughout our whole observable universe.
There's a lot more here in the local group. So.
Exactly. So the Copernican principle would state that there should be nothing special about our solar system. It just be one of many. So
Right.
why should every solar system look like ours? There should be a whole range. We just happen to live in one particular one. Now, you can go a little more than that and state, well, why is the Earth at the distance it is from our sun? Because if it wasn't, we wouldn't be alive to talk about it.
We wouldn't be allowed to talk about it. Nothing special there. We wouldn't be here.
Yeah. So there's lots of other planets in our universe where life as we know it would not be able to live because the conditions are too inhospitable.
Right. So this would be an example, yeah.
So to have solar systems, exoplanets that exist, that don't, if you like, obey the laws as we lay them down, is normal. It's a normal process in science. In fact, I would argue that's how science progressive
Right.
is to find these type of things that turns over your ideas, the paradox shifting views that we come across once in a while through discovery, observations, and or experiments, for example.
I mean, the finding of this planet, there's the other two things. It upends the models that we have for how planets form because there's two major models. One is accumulation. Basically, everything starts out as little droplets or little pebbles or little clumps of dust, and these combine slowly over time to form a planet.
Now, Robert, how long does that take on average?
I haven't kept up with it as much as I probably should, being this is my area of interest. But the usual models show that this type of thing, accretion is called, take about 400 million years.
Okay, so it takes many millions of years, but not billions of years.
But not billions of years, right.
And the material is collected because of gravity is the only thing you have to...
You just have to have gravity, yeah.
Yeah, so gravity's doing its thing, right? So unlike ice cream, it only comes in one flavor. It's always an attractive force.
There you go.
Okay. But what's the other ideas that we have besides the
Okay.
core accretion type of thing?
The other major idea about how planets form is called gravitational or density instability. So in other words, this is saying that there are regions of the gas disk that simply the density is higher than the surrounding disk. And that these then act kind of like a vacuum, sucking in all the material around them. And basically they become denser and denser, and now kind of like the accretion model, gravity takes over and pulls in more like a vacuum. Yeah. A vacuum cleaner, I should say.
So how would you explain this particular example here of this exoplanet star system?
Okay. Personally, I would lean towards this one being explained by the instability model more so than the accretion, simply because you have a massive planet, so it had to be. Let me say that the instability model has been able to form planets in under, pardon, under 100 million years, so much faster than accretion. The reason that's important is this planet is close to its star. So it had to form quickly, or else all the gas and dust would have been blown away by the solar wind.
Okay, so the star itself, when it turned on,
Produces.
when hydrogen fusion began in its core, it releases a tremendous amount of energy.
A lot of energy.
And that clears its environment, its immediate vicinity of leftover debris.
Think about it this way. There's two pressures involved. There's radiation pressure, simply from light slamming into the particles, essentially. And then there's actually that heats things up. So now you've got thermal pressure pushing it outward.
Right.
So, yeah,
So
a
if
lot
this
of energy.
so if this object did not form to the point where its own gravity can prevent itself from being torn apart or evaporated,
Yeah, evaporated.
then it'd have to happen relatively quickly before that object turned into a star
That's it.
and nuclear fusion begins.
And so Wonder Goon asked the next question, which is, are the two models of planet formation mutually exclusive? If you ask the big people in both camps, yes, they are. However, no, they're not really. You could have, the problem with the instability model is that thermally, these instabilities are not stable themselves. They dissipate. They have to dissipate due to thermodynamic properties and conditions. I won't go into things like Tumor Q values and things like that. Just too in-depth for this show. But bottom line is these instabilities would have to dissipate over time, and relatively quickly, actually. So they form planets really quickly, but they themselves are not stable. Okay? The accretion model, on the other hand, forms planets very slowly, but you don't have any constraints about how long it can last, other than the fact that the dust and debris are cleared out by the radiation pressure of the star. So they're not mutually exclusive, because if you get a density increase in a region, then all the particles in that region are moving relative to each other slower. So they're going to slam into each other, or bump into each other, I should say, much more slowly, and could stand a bigger chance of accreting. Whereas if they were moving at different speeds from each other, they're probably going to hit and chip off. Think of throwing a rock at pavement. If you do it on a dark night, you can see that sparks fly. So little chips come off. So the density instability could slow things down to where the accretion model can now make things stick. And so they're not mutually exclusive ideas, but there's so much time and effort invested in a lot of these things that people do act like they are.
Now, why can't you have a situation where the planet forms much further away from the host star, and then through planet migration ends up wandering towards the center, being in the orbit that it has today?
And absolutely, you could have those. Basically, think of it as air resistance. There's gas and dust in the disk around the star, and as a planet forms, it's losing energy to that gas and dust. And so that would cause it to spiral into the star, towards the star. The problem is eventually it reaches that zone where all that gas and dust is cleaned out, but it's now moving towards the star. So how do you stop it? And that's a problem. So the fact that it can move and migrate through the disk probably happens. But how do you get that motion to stop once it started?
In fact, we could speculate further if we go back to our own solar system and say that early on in the beginning, when planets were first forming, there might have been several planets that formed, were on this migration path, if you like, and ended up going into the sun and being vaporized, and has now become part of our sun.
And in fact, from other stars, looking at their spectra, there's evidence that that is exactly, that has happened to those stars, because they have high metallicity, higher than they should from their spectral type. And so the current thought is that they're contaminated by a planet that they swallowed, essentially.
So that debris becomes part of the outer atmosphere of that star, and we can detect the signature of that when we look at its spectrum.
There you go.
Now, and the other thing is that means what's left over today, the planets, is whether you think of it as 8 or 9 planets and everything else, it's just the things that are on more stable orbits.
Right.
That they didn't decay to the point where they ended up going into the sun, essentially.
That's it. Or they weren't interacting with each other to the point that one of them got flung out, because we could have had many more planets. Some of them were thrown into the sun by the gravitational interaction with the disks and other planets. Some were thrown out of the solar system.
And we know that hasn't happened in the last roughly 4.5 billion years, because that would have disturbed the present orbits of the planets that are around today, and we would notice that. Right?
We would notice that. They'd be more elliptical, less circular than they are,
Yeah.
and they'd be higher inclination, higher out of the sun has an equator too, and inclination refers to how steeply they are out of that equator, that equatorial plane.
So you think of planets forming from ultimately a pancake-like distribution of material, then those planets more or less would orbit in the same plane
Right.
As all the other planets. So all the major planets then orbit in roughly the same plane, and that just really gives you information about the formation of the solar system to begin with.
There you go.
Yeah.
And so as they interact with each other gravitationally, there's a tendency to stretch their orbits out of circular and to kick them up in inclination up out of the pancake.
And that's not easy to do, because
That is not easy to do.
when we send space probes out to fly by to various planets or even to observe our sun, one of the probes was the polar orbiter that orbit the sun from above and below its pole, north and south pole, if you want to think of it that way. But it had to go out to Jupiter and get a gravitational slingshot from Jupiter to put it into a really high inclination orbit. But it took a lot of energy, so the probe really didn't have a lot of mass. You had to wait a long time for the type of trip to happen, right?
This is why people don't believe me a lot of times, but the statement has been made and is true. It would take more, in the case of nuclear waste, why don't we throw it into the sun? Because it would take more energy to change the angular momentum, the energy of the satellite, essentially's orbit, to send it into the sun than it would just to send it to the outer solar system.
Right.
It would take more energy to send it into the sun. Well, if we just launch it and it falls, that's not what happens. It's going at the same speed as Earth. So it would stay in orbit with Earth. That's not what we want.
Yeah, you'd have to, in simple terms, you'd have to expend the amount of energy to slow it down to a stop and then let it fall towards the sun.
Let it fall.
But that slowing down is what would cause trouble. Of course, that not even talking about the risky proposition of launching radioactive material from the surface of the Earth and hoping your rockets never blow up halfway up.
Your rockets don't blow up, right?
We laugh about it, but that could be devastating, obviously, to the climate here on Earth.
Yeah.
But just to show you how unique this system is, what does this slide illustrate, Robert?
Okay. This slide is showing mass ratio of the planet to the star. So mass planet over the mass of the star. And along the bottom axis is the orbital period, how fast the planet is going around the star. So usually that mass ratio is about 3.5 times 10 to the minus third, about three 2 zeros in front of the 3.
Yeah.
And and then the decimal point at the front of that.
Yeah, 3,000.
So 3,000th. Okay. So right there, this star system is, if you look at the vertical axis, is on the edge of that limit. It's actually still a little high.
So so people know for clarification, the red label LHS 3154b is the system we're talking about.
I should have said that. Sorry. So it's the one that's up high out of everything that's on the left side of the graph.
Yeah, so all the data points that are below it represents other systems that are at similar distances away from the host star.
Right.
But their the mass of the planet to mass of the star ratio is much lower.
Right.
Because that is a logarithmic scale.
That's a logarithmic scale.
not a
So it's
linear
powers
scale.
of 10.
Yeah. So this object is highly unusual, this exoplanet.
It's really strange. It's the mass ratio between it and the star is wrong. and it's close into the star, which is wrong. So this is calling into question all kinds of things about how we believe planets form. So
Yeah, so as we say there, it is not consistent with those two general theories, as you mentioned, the core accretion and the gravitational instability model for the formation of planets. And that's a good thing, because once again, it gets back to what we started talking about at the beginning, that we're always looking for things that are different, that are out of the norm.
you make your career by studying what is different, what is wrong with what we've been saying.
And speaking about making your career, if you want to make your career in the STEM fields, please consider coming to the University of North Dakota. You can either come here in Pleasant, be on campus in the wonderful time of the year in the winter.
Yeah.
Or, I mean, a lot of the activities happen indoors. I mean, some things happen outside, but a lot of them happen indoors. So who cares what the weather is if you're inside? But also you can do things online, of course. We have the technology that we didn't exist, in years past, where maybe you dreamed of attending the University of North Dakota and you just can't come to Grand Forks. But now you can through the magic of the internet.
Or let's be honest, you just hate the cold.
Oh, yeah, you can do your schooling from the southern tip of Florida if you like.
There you go.
And still take classes from the University of North Dakota and get that great education.
Absolutely.
Well, if you want to find anything new, of course, about us, stay tuned to the future podcasts. Like we mentioned at the top of the show, we will be going to season number 2 starting next year. And the first podcast will be January 9th. So January 9th is on a Tuesday and the same time, 3 p.m. Central Standard Time. In the meantime, if you have any questions for Robert and I, you can always, we don't hide, you can always find us.
You can find us.
And feel free to send us an email to either complain or suggest topics that you'd like to see covered, or maybe guests we could try to, and we can always email famous people and say, do you want to be on our podcast? And they would probably just say, no, go away. Or they don't even answer us, right?
That or their agent will sit there and say, yeah, but that's $1,000 at least to appear, or 10,000 even.
I'll give you all the money in my right pocket.
Right.
In fact, it is equivalent to what's in my left pocket. Nothing.
Lint?
Lint, yeah. Well, we always end our podcast, Robert, by a quote.
A quote.
And today it is fitting, I think, to do the master of all physicists, Albert Einstein.
Sounds like a good way to close.
And here's the quote. The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. He to whom the motion is a stranger, who can no longer pause to wonder and stand wrapped in awe, is as good as dead. His eyes are closed. So keep those eyes open, and please listen to us in the future. Thank you very much.
See y'all next year.